Everyone is ready? Yeah, I can already feel the energy and the enthusiasm flowing. Thank you all for being here today. A big shout to some guests that we have sitting in the back, the SHAD program high school students. Thank you for coming here. Thank you all, Women in Physics Canada Conference participants and guests for being here for a long-awaited talk. And we're so honored and thrilled and excited to host you, Jocelyn Bell Burnell, Dame Jocelyn Bell Burnell, for the Women in Physics Canada Conference keynote lecture at the University of Manitoba. Jocelyn is known for her discovery of pulsars as a graduate student in 1967, a discovery that opened a whole new field in astrophysics and continues to impact many new areas in astronomy and physics and applications in everyday life. This discovery led to the 1974 Nobel Prize in Physics to her thesis supervisor, Anthony Hewish. Now, pulsars, you'll hear about them directly from Jocelyn, the discoverer of these objects, but they're neutron stars, some of the most amazing objects known in the universe. They could be some of the strongest magnets in the universe. And to me personally, they are the dearest astrophysical objects to my heart. Despite their discovery over 55 years ago now, they continue to fascinate us, to puzzle us. And in particular, just recently in 2017, gravitational wave detectors have detected gravitational waves from two colliding neutron stars, opening yet a whole new field called multi-messenger astrophysics. So back to Jocelyn. Not only she's an incredible scientist, but she's also an incredible human being. She's a role model to so many of us around the globe and a champion of equity, diversity, and inclusion. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics. Following the announcement of the award, she decided to use the $3 million prize money to establish a fund to help female, minority, and refugee students to become research physicists. The fund is administered by the Institution of Physics. In 2021, Jocelyn became the second female recipient of the Copley Medal, which is the most prestigious award of the Royal Society, which is given for sustained, outstanding achievements in any field of science. She's now affiliated with the University of Oxford and Mansfield College, and Chancellor of the University of Dundee, and was the first female president of the Royal Society of Edinburgh, Scotland's National Academy. As you can imagine, she's much in demand as a speaker and a broadcaster. In her spare time, she gardens, she listens to choral music, and is active in the Quakers. She has co-edited an anthology of poetry with an astronomical theme, Dark Matter, Poems of Space. So thank you, Jocelyn, for making it here all the way from Oxford. Despite all the hiccups you encountered in your travel here, we're very glad that you made it in time, and we're so much looking forward to your talk. The floor is yours.
Thank you. Thank you very much for that very generous introduction. It's wonderful to be here. It's wonderful to be traveling again after COVID, and I've not been here before, so this is really enjoyable, and an excellent conference going on as well. Now learn to use this. Right. So I'm going to say a little bit about my background. I'm then going to tell you about the discovery of pulsars, an accidental discovery. One of the spin-offs that I hadn't anticipated of having discovered pulsars is every so often somebody comes up to me and says, you know, I nearly discovered pulsars, and tells me the story. And actually these stories are of interest and revealing as well. So I hope from the combination of stories I tell today, you may get some sense of how, at least in astronomy, research progresses. I'm also going to spend a few minutes just thinking about the factors that led to the discovery, just in case you haven't picked it up from the talk as I went through the story. So I start with my background. My accent is not Southern English. I started life in the north of Ireland, the British bit, at least currently. Spent quite a bit of time in Scotland, although I now live in southern England. I started my academic career by failing the first important exam I had to do. There was a system in Britain that all children sat an exam at age 11 and a bit. And it was believed that at that stage you could tell whether a child was going to be academic or more practical and technical. And secondary education was organised in two streams, what we call grammar schools for those who had passed and technical colleges for those who hadn't. And I failed that exam. That meant that if nothing else happened, my future was to train as a secretary or maybe an unqualified nurse or a filing clerk or something like that. Well, my parents weren't settling for that. They intervened, and I was allowed into the academic stream of the next level of school on the understanding I was only there for a couple of years because at age 13, I was being sent away to boarding school in England. Some of you may know that Northern Ireland is not a very happy place. The Protestant and the Catholic communities are well separated, except when they fight and kill each other. It's not an easy community and very polarized in every way. And our parents decided that all of us kids would have some of our education in boarding school in England. So I was due to go away to boarding school at age 13, and they let me into the academic stream. And I can remember the first week in this academic stream of the big secondary school, the grammar school. Up till then, we'd been in one room with one teacher and 4 or 5 kids in each year. And suddenly I'm one of 50 or 60 kids divided into 2 classes, and we're doing different subjects and moving from classroom to classroom and lots of different teachers. And I remember particularly the Wednesday of that first week in that more senior school. Message went round the first year class, this afternoon, boys to such and such a place, girls somewhere else. And I thought, Wednesday afternoon, sport. That's why they're separating us. It wasn't. They sent the boys to the science lab and the girls to the cookery room. Everybody knew, note the quotation marks, everybody knew that girls were only going to get married and be stay-at-home wives and mothers. They didn't need a fantastic academic education. They needed to learn how to cook and sew and clean the house. And that's what this intellectual grammar school was proposing to teach us girls. My parents had promised me I'd get to do science when I got into the big school, so I was distinctly miffed. Tried arguing with the domestic science teacher, but she wasn't having anything of it. But when I told my parents that evening, they hit the roof and phoned up the head teacher. The local doctor had a daughter in the same class. He phoned the head teacher, as did one other set of parents. And the next time the science class met, there were 3 girls and all the boys. And I don't think that teacher had ever taught girls before. We were clearly dynamite. He made us sit in the front row with our desks right up against his desk, because clearly we'd make trouble otherwise. We did physics that first term, and I loved it. And I can remember one particular bit. We were learning about motion in a circle, centripetal force and centrifugal force. I have borrowed one of my father's library books, a book by somebody called Fred Hoyle about the universe and astronomy. Fred Hoyle, Frontiers of Astronomy. And in Fred Hoyle's book, I'm reading about galaxies, great systems of stars, 100,000 million stars that rotate. And here at school, I'm learning about things rotating. I think, I could be an astronomer when I grow up. Then somebody pointed out to me that astronomers work at night. And my spirits sank, because I knew I needed my sleep. I couldn't work at night, certainly not on any sort of regular basis. So, I can't be an astronomer. Yeah. And then somebody somehow mentioned, or I got to hear about radio astronomy. Astronomy done at radio wavelengths. These days, astronomy is done at many, many wavelengths, right across the spectrum. Gamma rays, X-rays, ultraviolet, ordinary light, infrared, microwave, and radio. Originally, it was just that tiny bit of the spectrum that's visible, but today we do it right across the spectrum. So somehow I got to hear about radio astronomy. I thought, right, I'll be a radio astronomer. And I went through high school intending to do a physics degree, because I thought that's a good preparation for any kind of astronomy, particularly radio astronomy. And if I can't get a job as an astronomer, I'm sure I can get some other good job. So I did physics at school, and then went on to university to do physics. Most of my secondary schooling was in a girls' boarding school. Parents were keen to get us out of Northern Ireland for some of our education, and we all got sent away to boarding school in the north of England. Girls' schools had trouble getting good science teachers. I can remember our chemistry teacher. There was a chart of the periodic table up on the wall above his head, listing all the elements in a sort of grid pattern. And we said to him, why is that sort of laid out like that? And he said, God made it so. I don't think he understood the electronic structure of atoms. Girls' schools had difficulty getting good science teachers. Our physics teacher was an excellent teacher. He'd come out of retirement for a second time to teach us. And he was a very, very clear teacher, albeit with a Yorkshire accent. So we learnt gems like you slew up on a slope. Do you understand that well enough? He gave me free run of the physics laboratory in the evenings. This is a boarding school, we're living there. Health and safety would not permit it these days, but and I decided to make a great big plot of the magnetic field of a bar magnet. So I went to the magnet drawer, chose my magnet, put it on the bench, got this big sheet of paper. Physics teachers probably know what's coming next. I didn't, and started plotting. And of course, I didn't get it done in one evening. Next evening, come back, get out my bar magnet, and I can't get it aligned with what I was doing last night. Magnetic field comes through desktops. Don't work on top of the drawer where the magnets are kept, because if somebody's been into that drawer during the day, all the magnets will have got rearranged, and the magnetic field here is different. Lessons that you learn for yourself. are always very powerful lessons. So in spite of some good teaching and quite a bit of rather poor science teaching, I got a place at the University of Glasgow to read physics. I ended up the only female in the honours physics class, 49 men and me. And it was the, quote, tradition that when a woman came into the lecture theatre in Glasgow, it was all woman, all wooden, no carpets or anything. All the guys would go. Can you imagine 49 guys doing that and stamping, whistling, catcalling each time you came in? I learned not to blush. You can control your blushing. And sometimes it's necessary to be able to do so. I duly got my physics degree. For astronomers in the audience, my final year tutor was a funny little man called Ron Drever. He was that stage looking to see if the mass of the electron changed when the galaxy went overhead. He subsequently went on to work in gravitational radiation. And I was so impressed by this man, I made a mental note to keep an eye of any field he worked in. And so I was watching gravitational radiation right from its birth, or I should say the detection of gravitational radiation. I knew we detected someday. I wasn't sure I'd be around to see it, but it's happened. Yaha! Whole new spectrum opened up. He wrote me a very good reference. I had intended to go to Jodrell Bank. I'd worked there as a summer student. This is part of the University of Manchester with a great big radio telescope. But I didn't get an answer. And while I had worked there one summer, I had been told that they would never take a woman. There had once been a woman student, and she and one of the young men had put the dormitory accommodation to a use for which it was not intended. He bragged. Sir Bernard Lovell, the head of the laboratory, said, "No more women." Interesting which sex bears the brunt of these mutual encounters. So I wasn't going to get into Jodrell Bank, I reckoned, and I applied to Cambridge, which is a huge step for a kid from the provinces like me. And I must say, when I got to Cambridge, it was really, really daunting. It was full of young men who'd had expensive schooling, who were full of self-confidence, were absolutely sure they were entitled to be in Cambridge. In fact, Cambridge owed them, they were so good. And there were very, very few women. And very, very few people from the north and west of the country, which is where I was coming from. So when I got there, I thought, they've made a mistake admitting me. They're going to discover their mistake, and they'll throw me out. But until they throw me out, I'll do my very best so that when they throw me out, I'll know I haven't wasted the opportunity. It was just that I wasn't bright enough. This, they've made a mistake admitting me, is what's called imposter syndrome. And it's now quite well recognized. And if any of the younger people here find themselves in such a position, I'd recommend my strategy. Work your very hardest so that if they do throw you out, you'll know you've done your best. And they probably won't throw you out. But of course, you don't feel confident enough to know that. So I was working very, very hard in Cambridge. Discomfort increased slightly when, within the first week, each of the new grad students was given a set of tools. These are my tools. Still have them. They were the first tools I ever owned. These are not microelectronics tools. These are full-size, full-weight wire-working tools, because I'm going to be doing quite a lot of heavy work. I spent the first 2 years as one of a group of about 6 people building a new radio telescope. I'll show you a picture of it in a minute or two. My particular responsibility was all the cables and connectors and transformers, because when you go from cables of one impedance to cables of another impedance, it's like the signal has to meet a step and you have to help it over the step. It was a huge antenna. It covered an area of 57 tennis courts. So really, really big. Lots and lots of wooden posts, 120 miles of wire and cable, over 1,000 wooden posts. It costs £12,000, which I guess would translate as about $15,000, maybe $20,000. Not millions, thousands. So it was cheap, even by 1960 standards. This particular photograph, this is me. This is my technical assistant, Don. We've got some low-loss cable which stretch from here down to another little red and white hut there. I've spent some of the Cambridge winter sitting in this little hut, putting plugs and sockets on the ends of the cable and on the other ends of the cable, and we're now checking the impedance, checking that the contacts are good. So I've got a slotted waveguide here. Working in the field is surprisingly hard work. Even soldering in the field is hard work because the wind cools the soldering iron. You know, it's not trivial. This is the finished antenna. The most obvious things are the wooden posts. Their job is to keep everything up above wet grass. And most of the action is up here at the top. You can see some copper wire. There was miles of copper wire. Operated as an interferometer. It's really very simple. A bit like a diffraction grating with lots of rows, lots of lines on it. University of Cambridge at that point had one computer. This is about 1967. That one computer was pre-transistors, and it occupied a whole room. And very few people could have time on it. It had memory like your laptop, or maybe like your last laptop. And very few people could use it, and we didn't have time on it. We also were still using vacuum tubes, what we call valves in Britain. Transistors, unreliable, noisy. We use valves. And they did have one advantage. If your radio receiver is misbehaving a bit, what you go and do is that. And that actually serves to reseat the vacuum tubes, the valves, and quite often makes it work. But we didn't have access to a computer. Just briefly, what's going on here? Way up top in this diagram, way up there, there's a quasi-stellar radio source. My job was to find more of these. They were very, very new, sexy, and puzzling. And the signal from this quasar comes down to a radio telescope, and as it comes through the space between the sun and the planets, it's coming through a plasma called the solar wind that's blowing out from the sun. And this plasma is not smooth. It's got clouds with higher electron density. For the physicists, it actually acts like a diffraction grating, but it's a diffraction grating that's blowing out all the time. And so some of the time a beam comes to your telescope, and some of the time the telescope doesn't pick up a beam, and then the next beam comes and then it doesn't. And the intensity you receive jumps up and down like this, quite fast. That's 1 second. It turns out that quasars, which at that point were the very sexy object, are very compact objects, whereas radio galaxies are quite extended. And when you have a pattern like this, an extended object, you see through some of the clouds and some of the gaps. But a compact object, you sometimes see through a cloud, sometimes see through the gaps. So a compact object keeps changing its brightness, scintillating. So this turned out to be a neat way to pick out the compact objects, or the quasars. you look for objects whose signal is fluctuating like this. This is 1 second. Which means you've got to observe with a short time constant, a short integration time, or you smooth out the fluctuation you're looking for. Which means your signal to noise is poor because you can't integrate over a long time, so you need a large area of radio telescope, which is why that radio telescope was the area of 57 tennis courts. So spent 2 years helping build this thing. Most of my work was with the cables and transformers and plugs and sockets, but I did a bit of hammering posts into the ground, and I could swing a sledgehammer. I was also playing field hockey at the time, and I could hit the ball from one end of the pitch to the other. And the rest of my team would sort of watch the ball go by and say, "Oh, Jocelyn, never thought to get running," but never mind, their problem. The university at that time had one computer. University of Cambridge, top university in the country, it's got one computer. Computer did not have transistors in it because transistors were too new. It had vacuum tubes, and it occupied a whole room. It had memory comparable to your laptop, and very few people could have time on it, and we didn't. Our data came out on rolls of paper chart, and here we are, rolls of paper chart. There was 30 meters, 100 foot of this stuff every day. I took 4 days to scan the sky, and then I'd start again, another 4 days, and another 4 days. So each sky scan was 400 feet, 120 meters of paper. And by the end of 6 months observing, I had over 5 kilometers of this stuff, which I analyzed by hand. And remember, I'm scared they're going to throw me out. I'm being very, very careful. I am checking everything on that chart that looks at all peculiar. Finding lots of the quasars, it was very good for that. I think when we started, there were perhaps about 20 quasars known. By the time I'd finished, there were about 200. So it was very, very successful from that point of view. So, yep, we were doing repeated mapping of the sky. Quasars were very compact. They would show this scintillation. And what we do is spend 4 days scanning the sky, or spend 4 days, telescope set on that declination, sky goes past. Jocelyn, change the declination, sky goes past, change the declination. So we spend 4 days with 4 beams mapping the sky, and then we'd start again, or I'd start again. So we were regularly surveying the sky. And we had a very short integration time because I'm looking for objects whose brightness fluctuates, and I don't want to smooth that out. And it was very successful in that before I started, we knew about 20 quasars, and by the time I'd finished, we knew about 200. So it really delivered that radio telescope. But I was being extremely careful, paranoid, I think. And in amongst the scintillating quasars, and in amongst the inevitable radio interference, there was something else. Radio interference was quite a bad problem then. Cars were very badly suppressed. And every time a car went down the local road, it'd go on the radio telescope. But you got to recognize it. And pirate radio stations discovered this radio band that had been kept clear, for them, of course. And it was quite hard to get some of them shifted, turned off. But mostly we did pretty well. And because I'm being so very, very cautious, there's a signal that I don't always understand. What have I done? Okay, press the right button. This is low-level interference. And this is a signal I don't understand. And for the physicists in the audience, I'll sort of explain why they look different. Here the spikes go up and down. Here the spikes go mainly upwards. Here, at least people at the front, can see that between the spikes you can see bits of chart. Whereas at least the left-hand end of this, there's no way you can see the chart between the spikes. You're doing Fourier analysis in your head at this point. To say you can see space between the spikes says it's lower frequency than this one where you cannot see space between the spikes. And you're commenting on the amplitudes. Here they're positive and negative, and here they're positive only. That is Fourier analysis. And you've probably done it in your life without realizing, but you have. So these two look different. And I'm a little bit bothered by this one. Interference is forever with us. Nothing much you can do about it, but just discard that bit of chart. But this doesn't look like interference. And after I've seen it a few times, my brain says, you've seen something like this before, haven't you? You've seen something like this before from this bit of sky, haven't you? And then it's easy. I'm surveying the sky in strips, declination strips. And each chart for that declination, after I've analysed it, is rolled up and put in something like a shoebox, labelled with the declination. So when my brain says, you've seen something like this before, haven't you? I go for that shoebox and get out all the previous times we scanned that bit of sky. The grad students were in an attic, and there was a wonderfully wide sort of corridor down the middle between our desks. So I tell all the guys, all the rest of the occupants were guys, don't move guys for a minute, please. And I get out this box for that declination strip and spread them out on the floor and line them up. So yeah, it was there. I marked it with a question mark. Wasn't there that time, not that time. I think it's there, though I didn't notice it. I've marked that one. And look, they're all at the same right ascension. They're all from the same bit of sky. At this point, I go to my thesis advisor feeling quite proud of myself, and he basically says, you bloody fool. All this, whatever it is jammed in about a 1/4 inch, 5 millimeters. We can't see what's going on. We need an enlargement. And with chart paper technology, an enlargement is easy. You run the paper faster under the pen, and it all gets spread out. But I can't leave the chart recorder running at that speed forever, or it gets through the whole roll of paper in 20 minutes. And guess who lives at the observatory putting a fresh roll of paper in every 20 minutes? Next best idea, grad student goes out to the observatory at this point, switches to a higher speed recording, lets it run, and then switches off. And I did that for about a month and made high-speed recordings of receiver noise. The thing, whatever it was, it disappeared. And of course, my supervisor was cross. If there are grad students or potential grad students in the audience, you need to know everything is always your fault, according to the supervisor. Don't take it personally. Finally, I got it. And this is that first recording, albeit labelled afterwards. The bottom line is 1 second time marks, and the upper trace shows the signal. And you can see along here that it's equally spaced. Indeed, there's probably one missing there, and that's equally spaced. And there's probably several missing there, and those are equally spaced. The label was added afterwards. Indeed, with a little bit of intelligence, you can know the label was added a long time afterwards, because it's got the number 1. You don't label the first one of anything number 1. It's only when you've got a second or more that you go back and label the first one number 1. And LGM was my nickname. It stands for Little Green Men. Wasn't really serious, but you had to call this stuff something. You couldn't talk about that funny signal at 1919 plus 23 all the time. And it's got this period of about 1 1/3 seconds. Pretty accurately 1 1/3 seconds, which was unfortunate because my thesis advisor reckoned it was probably some kind of interference. Somebody in the lab next door has a signal generator set with a period of 1 1/3 seconds or something like that. Well, I didn't agree with him because this kept sidereal time. This comes back 23 hours, 56 minutes later each day, or multiples of that if you don't see it for a few days. And most scientists don't work a 23-hour, 56-minute day, only astronomers. But, well, maybe it was some of the other Cambridge astronomers. Our radio telescope site was as quiet as we could possibly make it, radio quiet as we could make it, but it was a bit suspicious. It did look very man-made. So, no, it couldn't be local radio interference. It's not Joe Dokes driving home from work in a badly suppressed car. He's getting off work 4 minutes earlier a day, 28 minutes a week. And by this stage, this has been going on for a month or two. And his boss hasn't noticed. It doesn't work. We asked a colleague and his grad student to see, which they had a radio telescope which worked at the same frequency as ours, to see if they could see it. And under oath of silence, they agreed. And I remember that occasion very well. The other grad student was called Robin Collins, and his supervisor was Paul Scott. And the way the telescopes were aligned, mine would see that bit of sky first, and then Robin's would. And there were 4 of us out there. I, my supervisor, Tony, Robin, and his supervisor, Paul Scott. And we stood by my chart recorder, and in came pulse, 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 pulse. It was behaving very nicely. And then we went and stood by Robin's chart recorder for his telescope, and nothing happened. And the 2 academics, Paul and Tony, started walking down this long laboratory. Robin stayed by his pen recorder, and I was padding along behind the 2 academics, trying to keep up with them in every sense of the word. So what could it be that shows in your radio telescope but not mine? Could it be black? No, it can't be that, but I wonder if, could it be da 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 da. And suddenly there's a shriek from Robin. Here it is! He had miscalculated by 5 minutes when his telescope would see it. And it did see it, and in came pulse, 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 pulse at exactly the same rate, 1 1/3 seconds. If he'd miscalculated by more than about 10, 15 minutes, we'd have all gone home and the story would be very different. But in many of these kinds of stories, there's a lot of, what if? It could have been very different. So it's seen by a separate radio telescope that has its own radio receiver. Now, it still could be some radio interference in the locality, but at least it's not that Jocelyn has wired up the radio telescope wrong, which is what my supervisor was muttering about. But as we continued to look at it, there was an increasing conundrum. It's got quite short, steep pulses, so it must be small. But it's also keeping the pulse frequency, pulse rate, very, very steady from day to day to day. It's not getting tired. It's got big reserves of energy. So it's big and it's small. Yippee, very clear. And it took us a long time to kind of believe that one, sort that one out. A colleague borrowed my radio telescope, and 2 of the receivers tuned one up in frequency slightly and one down in frequency slightly, and observed with these 2 receivers. The argument was, as a radio wave travels through space and to the Earth, it passes some free electrons, electrons that are not bound in atoms. And those free electrons cause what's called dispersion. The optical version of this is a rainbow, the way light is split into its different colors. The radio version of dispersion is that the higher radio frequencies appear before the lower. And if you can see that at the higher frequency, the pulses arrive earlier than at the lower frequency, then if you've got an estimate of how many free electrons there are around, you can get an estimate of the distance. And we made a very crude estimate and deduced that this thing, whatever it was way beyond the solar system, way beyond the sun and the planets, but it's within our own galaxy. So it could be little green men. However, my supervisor argued, if it is little green men, they probably live on a planet that goes round their sun. Now, for the moment, you're all the earthbound radio astronomers, and I'm a little green man, and I'm going round my sun. And I'm going beep, 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 beep. And as I come towards you, it goes beep, 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 beep. It's what we call Doppler shift. So, Jocelyn, keep observing. We want to look for a Doppler shift. So I kept observing. No Doppler shift. Very hard to explain. Doesn't seem to be radio interference, because 2 radio telescopes have seen it from the same bit of sky. And then I suspect I found a second one, looking at traces on my paper charts, my chart recordings. It's transiting at about 2 o'clock, 3 o'clock in the morning. It's December the 20th, almost Christmas time. And later that morning, I'm due to travel to Ireland, to my parents' house with my boyfriend, to announce my engagement, to be married, our engagement. I've got to be there. But I've also got to observe this thing. So 2 o'clock, 3 o'clock in the morning, I go out to the observatory and set up, and bless it, in comes pulse, 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 pulse. The first one pulsed at 1 1/3 seconds. This one was pulsing at 1 1/4 seconds. Similar, but sufficiently different that you really think you've got a second of whatever these are. My supervisor kindly kept the survey running while I was away over Christmas in my parents' house with my fiancé, and he piled the charts unanalyzed on my desk. I came back after Christmas. He was in a meeting, but it was quite clear. Oh, and I was wearing an engagement ring. Ladies, I don't recommend wearing your engagement ring to work. It sends a signal that you're distracted, that you might even be quitting work. But I hadn't thought that one through, and I was very proud of that ring. Tony's in a meeting, but he's kept the survey running while I was away, piled the charts unanalyzed on my desk, and it's quite clear what work I need to get on with. So I sit down and start doing chart analysis. And I'm nearing the end of one chart and sort of, which one's that? It's not either. It's not either. Whoa, have I seen this before? Let's get out the charts for this bit of sky. The charts are kept in shoeboxes labelled with the declination strip on the sky. Out come the charts, fling them along on the floor. No, maybe. Oh, I marked that one with a question mark. That was very clever. No. Oh, and there's another question mark. Oh, another question mark. This is another one. Wow. Okay. I'll just finish this particular piece of chart I'm analysing and then try and make sense of all this. So I've got about 1 metre of chart left. Here's this thing that I've just found. What? Is that another one? A metre apart, am I? Hecate. Find the shoebox for this lot, get them out. Yeah. Oh, right. At that point, supervisor appears, stands at the end of the desk. Hello, Tony, look at this, look at this. This one's got 1 1/3 second, 1 1/4 second. And look, here's another one. Oh, thank you for keeping the survey running over Christmas. Thank you for piling all the charts unanalyzed on my desk. Huh. How many more have you missed? Go back through all your old records. There's now about 5 miles. You still work in miles in this country? 8 kilometres. There's about 8 kilometres of these paper charts he just blithely told me to go through. And I do ultimately go through them and ultimately go out to the observatory and confirm these other 2. So we now have 4. 3 of them are pulsing around about 1 1/3, 1 1/4 seconds. The 4th one has a period of about 1/4 of a second. So it's clearly quite a bit faster. But it is good to have more than one. This begins to look real. This begins to look like some population that we hadn't dreamt of before. We duly wrote up the first one for publication, with the 2nd, 3rd, and 4th following in another paper. And such is the clout of Cambridge University that the head professor, Martin Ryle, was able to phone up the editor of Nature and basically say, hold the press, we've got something interesting coming for you. Nature did publish it, and just before that edition appeared on the Friday, about the Wednesday or the Thursday, Tony gave a colloquium in Cambridge, gave it a very titillating title, and every astronomer in Cambridge came. And Tony went through what we'd found and told him mainly about the first one, which was going to be in the paper in Nature the next day, and alluded to the others that were similar but not identical. There were 2 possible mechanisms for what this was. The first mechanism involves a rotating thing with some kind of beam, which is the picture we now have. Think of a lighthouse beam sweeping around the sky. Every time the lighthouse shines in your face, you see pulse, pulse, pulse. That's the picture we now have, we believe to be correct. But another possibility is there's something vibrating. And for the astronomers, he was thinking of a star called a white dwarf. A white dwarf vibrating. And each time it vibrates outwards, it launches a shock through its atmosphere. It's a plausible mechanism. The way you tell the difference is watching what happens afterwards. With something rotating, it gradually gets tired and grinds to a halt. With something vibrating, as it gets tired, the amplitude gets smaller, but the frequency gets faster. So the pulses would come faster. But we didn't have enough data to see any change in the period ourselves. Tony favored this model. He reckoned it probably was a compact type of star called a white dwarf, and it's vibrating and it's launching shocks into its atmosphere, which somehow, mechanism TBD, somehow gives a string of pulses, equally spaced. So just before Nature actually published the paper, Tony gave this colloquium in Cambridge, and I say every astronomer in Cambridge came. And there's one astronomer you may have heard of called Fred Hoyle. He's written some very good science fiction books. Fred Hoyle came and sat in the front row. And at the end of Tony speaking, Fred was the first to speak. Tony put forward this idea about an oscillating white dwarf. And Fred, in his best Yorkshire accent, said, I don't think it's a white dwarf. I think it's a neutron star. And it turns out that Fred was right. Within 45 minutes, he's heard the evidence and hit the right explanation, as gradually became clear. He was a very, very able scientist. He did not love the radio astronomers because we were showing that the universe was evolving, and he wanted a steady state universe. So any way he could clobber the radio astronomers, boy, he used it. However, press took considerable interest in this discovery, and Tony and I did a lot of press interviews, and they tended to take a very familiar form. The interviewer would ask Tony about the astrophysical significance of this discovery. And then they turned to me for what they called the human interest. What were my bust, waist, and hip measurements? How many boyfriends did I have? Would I describe my hair as brunette or blonde? Ye gods. They were not in the least interested in a young woman as a scientist. You were a sex object. And Tony, I'm afraid, did nothing to help. So I just had to kind of bear it. In a sense, the photographers were the worst. You know, please could I undo just some more buttons, please, for the photograph? It was really, really horrible. They just could not accept that a woman was a scientist. Young women, sex objects, period. But one of the interviewers from the Daily Telegraph, a rather conservative newspaper, but otherwise quite respectable, came and said to us, what are you going to call these things? And we'd given that some thought. There were two possibilities: pulsating radio stars or pulsed radio stars. And we opted against pulsed, because that might imply an agency making the pulses, little green men. So we said, pulsating radio stars. And the journalist said, no, short name. What about pulsar? A bit like quasar, which we already had. And pulsars they became. And that's due to the science correspondent of the Daily Telegraph. How am I doing for time? Slow, oh dear, right. Can you take a little bit more? Yes. One of the delights of having discovered pulsars is every so often somebody comes up to me and says, you know, I nearly discovered pulsars, and tells me the story. And these stories, I think, are also of value, also of interest, but they show us how science works. So the first story is way back in 1957. We are in McDonald's Observatory, and it's an open night. McDonald specified that the observatory, the telescope, had to be open to the public one night per month, and it's one of those open nights. And the telescope is set on the Crab Nebula, which is the remains of a star that exploded in 1054 AD, observed by the ancient Chinese. And there's a funny little star in the middle of the debris of that explosion. And telescope is set on that funny little star called Minkowski's star. And the public step up to the telescope and say, oh, gee, wonderful, amazing, whatever the public said in 1957. And a young woman steps up to the telescope and says, that star's flashing. Well, we now know that that compact star in the Crab Nebula is the remains of the star that exploded in 1054 AD, and it is a pulsar. And it pulses at about 30 times a second, 30 hertz, period of 33 milliseconds. Have we any Canadians in the audience? Do you know that in Canada, the power supply, the lights, used to be at 30 hertz? And some people can see 30 hertz. There were some unfortunate Canadians who could see all their lights and everything. And it tends to be young women who can see 30 hertz. This is a young woman who is telling folk that that star in the middle of the Crab Nebula is flashing at somewhere around 30 hertz. It is. We now know it is. But nobody believed her. And nobody followed up. Except the summer student who remembered the story and continued to tell it. 2007, the Australians have an online catalogue of pulsars, as many as were known back then. And they suddenly get a very excited email from a US citizen, Charles Schisler. He said that while he was working for the US military, he was based in Alaska at the early warning system, looking for Russian missiles coming in. And when things were quiet, his boss allowed him to play around with the equipment. And he used the detectors, not the transmitters, just the detectors, sort of scanned the sky and reckoned he found some pulsing things. He had done an astronomy course at college. He found his college notes. He found the definition of right ascension declination. And he made a note, as well as he could, of the right ascension and declination, the sky coordinates of each of these pulsing sources that he's picked up with the ballistic missile radar receivers. And he's just discovered the online pulsar catalogue. And one of his things is in the Crab Nebula, and several others are known pulsars. So he sends a wildly excited message to the Australian astronomers. Here's his, As a United States Air Force technician during a one-year period back in 67, 68, at the early warning site in Alaska, I discovered 14 pulsing signals on our extremely powerful radars. Not related to our mission. My Air Force supervisors did not appreciate the possible scientific implications of my discovery. And the highly classified nature of our work made it impossible for me to publish, etc. But he could remember the definitions of right ascension and declination, the sky coordinates that astronomers use, and he has, to the best of his ability, got those sky coordinates for each of his pulsing sources. So he made the notes of their approximate location. 10 or 11 of them have been identified as being pulsars, as I've just discovered from the ATNF online catalogue. Possible that all of them were pulsars. The first one that I discovered back in 1967 was in the Crab Nebula, and may have been the first pulsar ever noted by anyone. I'm now 81 years old, but blah, 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 40 years ago. Well, bless that college lecturer who taught him about right ascension and declination. He came to several of our conferences. The Australians worked with him closely, and they do believe he was genuine, but he couldn't publish. The third story involves a female astronomer called Sue Simpkin. Sue was brought up in Canada at the time when the electric power supply was at 30 hertz. Sue was one of those young women who could see all the lights and everything doing this in Canada. Sue can see 30 hertz. By this stage, she's working in ultraviolet astronomy. Lo Vulture, an eminent Dutch astronomer, asked her to take a spectrum of the Crab Nebula source, the funny star in the middle of the Crab Nebula. Sue does so. She says it's pretty boring spectrum, but as she observes it, she can see waves going out. She tells Lo Vulture this, and he says, "No, you're imagining things." But when pulsars were discovered, he was man enough to say, "You saw the pulsar. You were probably the first person to see that crab pulsar." But she didn't publish because of his attitude. The last one, I'm not going to name the people involved. Although a number of them are no longer on this earth, they were always acutely embarrassed by this, what I'm about to relate. And so I won't name them, but they were radio astronomers. They're making a map of the whole radio sky, north and southern hemispheres, with big radio telescope. They don't own a big radio telescope, but they get a week on that one and 10 days on that one and some more time on that one. And they've just about finished. They're filling in the last little gaps in their survey. It's pre-computers. They're using pen recorders, chart recorders, and one of them is a bit sticky, a bit troublesome. It's 3 o'clock in the morning, and that troublesome, sticky pen recorder starts going whoop, 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 whoop. And the observer thinks, oh, damnation, and does what we always did to cure pen recorders. And it stopped going wheep, 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 wheep. So he said, oh, good. Put on his coat, went home to bed, and did not make an entry in the logbook. If he had, they could have claimed prior discovery of the pulsar 0329, because they were looking at that bit of sky, and it has a period relatively slow as pulsars go, which they could well have picked up with the equipment they had then. I think it's also a little bit sad that following the announcement of the discovery of pulsars, none of them was in a position to go back through their old recordings and see if they'd seen anything. So that one never got published in any sense, but is known within the community, you know, the folklore around. I want to end by paying tribute to an Italian astronomer called Franco Pacini. Alas, no longer with us. One of the great puzzles in astronomy was this object. It's called the Crab Nebula. It's the remains of a star that exploded in 1054 AD. And we know about it because ancient Chinese records record this explosion, because suddenly it became much more visible. They called it a guest star, but it was that star exploding. And what we see today is the debris from the explosion. Now, the explosion was in 1054 AD. The debris ought to have dimmed in the intervening centuries. The debris ought not to be visible now, and yet it is. Something is keeping that debris shining. And this was an exercise that kept some theoretical astronomers quite well occupied for a while, including Franco Pacini. He said, suppose that in the middle of the Crab Nebula there is a neutron star, a magnetized neutron star. The magnetic pole, if its spin axis is like that, the magnetic poles are offset so that as the star spins, this thing cones around, and it will give radio frequency waves at with this particular period. Depending on the electron density in the nebula, a signal at this frequency may or may not get out. If it doesn't get out, it'll get trapped in the nebula. It will keep the nebula energized and shining, and that's why we can still see the nebula umpteen years after 1054 AD. He was right, before the publication of Pulsars. So I really am going to stop shortly, but just going to spend a minute or two reflecting on the factors that led to the discovery when it was. We had our own telescope and our own receivers. We, so to speak, almost owned them. They belonged to the lab, but nobody else was using them. And I made it my job to understand how they worked, why they worked, what their foibles were, because it was part of my kit. I'm a graduate student, a research student. I've got time to follow up anomalies. Indeed, it's part of a graduate student's job. This was one of the first observations in radio astronomy that had ever been made with a short time constant. Mostly we integrated for 20 seconds, 30 seconds, a minute in order to get good signal to noise. But because I was looking for rapidly fluctuating things, the quasars, we were observing with quarter-second time constants, and this was one of the first of those. We didn't think anybody else was using similar kit, so we didn't feel under huge pressure to publish quickly in case somebody else does it first. We had a good address, the University of Cambridge. If you're going to find something really startling or dramatic, if you don't have a good address, if you don't have a reputation for reliability, no editor will touch it. But this was Cambridge, and it traded on its name. There was a phase in Britain for assessing research projects by how well they had met the objectives that they declared when they asked for funding. We hadn't declared pulsars as an objective. We didn't know they existed. Would we have been marked down for deviating from the objectives of the program we were funded for? Don't know. And I was working at a low radio frequency, much lower than was used normally those days. And also, people were tending to use long integration times to get good signal to noise. So I had low frequencies as an advantage and short integration times, good time resolution. Just for those who don't know what pulsars are, mass a bit more than our sun, 10 to the power 27 tons. Radius 10 kilometers. You can already see the densities, very, very high. Average density comparable with the density of the nucleus of the atom. A thimbleful of that star stuff would weigh the same as planet Earth. The whole of, same as the population of Earth. Because you've got a lot of material in a small volume, the gravitational attraction is very, very strong. If there was a mountain 1 centimeter high on these pulsars, the work you'd do climbing that 1 centimeter is like the work you do climbing Everest here on Earth. And similarly, the atmosphere is compressed. It's only 1 or 2 centimeters thick. Gravity will bend light. And with these stars, the gravity is sufficiently strong that you can see over the horizon because the light gets bent. Not sure why you'd want to see over the horizon, but you could. Gravity also redshifts light, so if there were little green men, the proverbial aliens, living on these stars, to us they'd look like little red men because gravity redshifts the light. Gravity also affects clocks, so if you went there with your best watch, you'd find that your watch was making 1 tick every 2 seconds rather than 1 tick every second because gravity was affecting even your good watch. There's also quite a strong gradient of gravity. So if you're coming into land and you come in feet first, because that's the ladylike way to land on one of these things, the force on your feet is a lot stronger than the force on your head. And your body gets stretched long and thin, and then I regret to say, broken up into pieces. So don't go visit a neutron star. There's very strong magnetic fields, there's huge voltage drops, and so the Lorentz force is huge. And again, it would do nothing but harm to the atoms in your body. Electrons and nuclei of the atoms would get stripped apart. So don't go visit a neutron star. And all this rotates as a solid body, with the rotation period being the pulse period that the pulsar shows. Today, the range of pulsar periods is between about 1,000th of a second and 10 seconds. For a typical pulsar with a period of about 1/10 of a second, milliseconds that is, not 10ths of a second, with a period of about 1/10 of a second, out at about 5,000 kilometers, the material is going at the speed of light. So they are very extreme. They're weak emitters of radio waves, but they're splendid things for testing Einstein's theory of relativity. Once you get 10 to the power 27 tons spinning, it's the devil's own job to make it change its period, and so it keeps pulsing very, very accurately. Current questions in pulsar physics: what's the maximum mass? We originally said 1.4 solar masses. We've now had to put that up to 2. It's probably got to go up a bit bigger. A number of these pulsars are moving quite fast across the sky. Have they got their own jet propulsion engines? Are they ejecting neutrinos out the back? Or is it because of an asymmetrical explosion that formed them? We don't know, but some of them move at quite a speed. And with that, I will stop, and with apologies for rattling on so long. Thank you for your attention. Your interest.
Thank you very much for this wonderful talk and walking us through your fascinating discovery of fascinating sources and reminding us of the importance of attention to detail in science. I guess one of the points in your key to discovery is your own attention to detail. Otherwise, that would not have been discovered. So, questions to Jocelyn, please go ahead.
So I'm wondering, when your PhD supervisor was so discouraging and wasn't really happy with anything you were doing, especially at the beginning, how did you keep your head up, and how did you manage to stay on the course and not give up?
Well, you've invested quite a bit of effort already when you're doing a PhD, and you don't want to throw that away. So it was really a case of, let's get this damn PhD completed and off somewhere else kind of thing. It was a wanting closure, basically.
Yeah. Thank you.
Thank you. That was an amazing talk. So I see a lot of parallels in the story of the discovery of pulsars and the ongoing discovery of fast radio bursts. Yeah. So I was wondering if you had any favorite theories of what they might be, and if you have any advice for Canadian astronomers who are trying to figure out what these fast radio bursts are.
Thank you. For those in the audience who haven't heard of fast radio bursts, pulsar astronomers these days are observing many pulsars, but the pulses can sometimes get confused with bursts of interference, radio interference. So they always check what we call the dispersion of the pulsar. How far away has it come from? If it's terrestrial interference, it'll be thousands of miles. If it's a radio pulsar, it'll be hundreds or thousands of light years away. So they're always checking the interference. And at, I think it was Green Bank, Duncan Lorimer in particular picked up a pulsar, or a pulse, a single pulse. And when he checked how far it had come from, the distance was huge. All the pulsars we have measured so far, I think this is still true, are within our own galaxy, the Milky Way. This was from way beyond the Milky Way. And what he had picked up was the first of what we now call fast radio bursts. There are things, we're still not quite sure what they are, which suddenly send out a short burst of radio waves. Some of them repeat, a lot of them do not. And Canada's playing a large part in this with the Large Radio Telescope. I've forgotten where it is. Is it Penticton? Yeah, yes. Penticton, thank you. It's doing really, really very, very good work. And we are finding a lot of these single isolated bursts. There are a few that repeat, but not a huge number. Mostly they're one-off. And so you, in a sense, you don't see it coming. You find it in your records afterwards. And I think the jury is still out about what these things are. We probably now know of, I would guess, a couple of thousand. Does that seem right to people in the know? Something like that. They're from all over the sky. Australians had an interesting diversion at the Parkes Radio Telescope. Who's got a microwave oven? Yeah. Do you know that if you stop your microwave oven by opening the door, rather than by pressing the stop button, there's a short burst of radio waves comes out, hits you in the chest. If there's a radio telescope nearby, it'll pick up that short burst of radio waves. And the Australian radio telescope at Parkes has a residence about a mile away, with a microwave oven. And if some of the people staying there stopped that microwave oven by opening the door, the Parkes radio telescope got what it thought was a fast radio burst. But they were all at the same distance because the signal scanned down in frequency at the same rate. And they finally pinned it down to the microwave oven. It's not wildly dangerous, but I recommend you stop your microwave oven by pressing the stop button in future. So there's been excitements like that have caused a bit of diversion. But I think we still don't know what these things are. I'm sure we're going to continue to find many, many more. And I'm not quite sure how we solve the problem until we hit lucky, in a sense. And we're finding some from beyond our own galaxy now, from other galaxies. Probably know of about 1,500 at this stage, and very, very few repeat. So they're really hard to catch.
Yeah, question there.
Thank you so much. That was an amazing talk. I've heard you speak on BBC and never in person, so thank you so much. And I just wanted to ask you the question to give you the opportunity. Every time I've heard you speak, you're so gracious with your referring to your supervisor and his Nobel Prize. And I wondered if you'd like to give us the real story or continue to be gracious. Thank you.
Yeah, I can remember the day of the Nobel Prize very well because I had moved, got married and moved, was working in X-ray astronomy. And our X-ray astronomy satellite, Ariel 5, launched at about 8 o'clock that morning. And we'd all gone into work. This was the X-ray astronomy group. We didn't have a video link, but we had a radio link and we heard the countdown and the launch and it all seemed to be working. That was about 8 o'clock in the morning. At noon, one of my colleagues came rushing into the office. Have you heard the news? Have you heard the news? And since I was due to be working on that satellite, I assumed, God, it's failed. It's gone in the drink. And it wasn't. It was the announcement of the Nobel Prize being awarded to Martin Ryle and Tony Hewish. Martin Ryle was the head of the Cambridge Radio Astronomy Group, and Tony Hewish was my thesis advisor. And he actually, my colleague who came rushing in, was expecting to see me very angry. But I wasn't, because I recognized immediately that this was a huge precedent. There is no Nobel Prize in astronomy. There is a Nobel Prize in physics, but until 1976, it had never gone to an astrophysicist, until they decided to award the prize to Martin Ryle, the head of the radio astronomy group, and Tony Hewish, my supervisor. And I'm quite a politician. I recognized immediately that this was a very important precedent and that other astronomers would get the Nobel Physics Prize in due course. And that has turned out to be the case. Quite often since 1976, some astronomer or other has got the Physics Nobel Prize. Interesting little sequel to that. A few years after that, the Nobel Committee gave the Nobel Prize to Joe Taylor and Russell Hulse. They were pulsar astronomers. They discovered the first binary pulsar, pair of stars, only one of which is a pulsar, if I remember rightly. And that's hugely important for testing Einstein's theories of relativity. And they recognized that, and they've done superb tests. And they got the Nobel Prize for that. Joe Taylor's quite a good friend of mine. They invited me to come to Stockholm with them for the prize ceremony and all the other celebrations. As a good colleague, of course, nothing to do with Pulsars. You should have seen the Nobel Prize Committee people. But we all behaved ourselves. And actually, having seen what a Nobel Prize winner has to go through, I'd recommend you go as a guest. Don't win it.
Thank you so much, Dame Jocelyn Bell Burnell. I really appreciate your talk, and I wanted to introduce myself as Alex Pedersen. I'm the manager for Equity, Diversity, Inclusion at the Arthur B. McDonald Institute for Astrophysics. And so I'm actually not a physicist, I am a geographer, so my extension of a thank you is also for making your talk so accessible and interesting for someone that doesn't have a background in physics. But if I may, in your talk, you've alluded to you clearly described having experiences of gender discrimination, of microaggressions, of gaslighting, of stereotype threat, imposter syndrome, and other significant hurdles over the course of your career simply for holding space as a woman in science. And I want to comment and commend you in this, as well as ask you the question of, over the course of your career, what excites you as a trailblazer now, looking back as well as looking forward, about the changes that have come after you for women in physics? How has physics changed for women since the start of your career?
The role of women in Britain in science and engineering and things like that is changing quite fast. And I was actually lucky enough to be a bit involved in that as well. There was a group of about half a dozen of us senior women meeting at our own expense after work in borrowed premises, sort of saying, how can we make science and engineering and technology better for women? And one of us said, you know, the heads of British universities are called vice-chancellors. You call them presidents here, principals? Anyway, vice-chancellors in Britain. She said, you know, vice-chancellors are competitive guys. They were all men at that point. If we create a prize for the most women-friendly university, they'll compete. And she was right. We were very, very poor. We had no funding. We were meeting in a borrowed room and paying our own expenses. But we got together enough money to buy a glass rose bowl. And we announced this competition for the most woman-friendly university in Britain. And a number of universities competed. We selected the one we thought was best, gave them a rose bowl. Repeated the experiment the next year, gave the rose bowl to another university. The first university had a program called Athena. The second university had a program called the Scientific Women's Academic Network, SWAN. We called our scheme Athena Swan. I think you've probably heard the name, judging by the way you're nodding. That's the origins of Athena Swan. We actually lost control of it, which was unfortunate. Research councils thought it was a great idea. Many bodies thought it was a great idea. Required universities to hold this award before they could get money. That works. But also kept adding more and more things in, more and more requirements. You know, how many women in each department, how fast are they being promoted, how many are sitting on interview panels, how many, lots and lots and lots of data. And the whole thing sank under the weight of data. It actually also moved to arts and humanities, where the question is, where are the men, not where are the women, but you know, same sort of issue. So that actually started quite a change. The scheme has collapsed under its own weight, so to speak, but it was the beginning of an interest in gender issues, particularly in science and engineering, which has continued in Britain, albeit perhaps not with quite the same force because there isn't money at stake, but at least there's a movement. Does that answer your question?
Thank you. Any questions from the back, from the SHAD students? No? Yes? Okay, and that would be the last question because we're running out of time.
So it seems like you've done, you've lived quite a successful life in some ways. You've made a very important discovery, but is there any, if you're to relive your life, would you do anything different?
I think as a young woman, I would have had more confidence, been less overawed, particularly at Cambridge. But again, I was where I was again because of the kind of training that was given to young women in my age. We were not expected to be assertive. We were expected to be nice little ladies and polite and docile. And that doesn't get you anywhere, ladies. You know, you do need a bit of muscle in your life. I think given the time I came from, I probably couldn't have done much else. But if I was starting again now, I would be more assertive.
All right. Okay. Thank you on behalf of everyone here. Thank you very much for this very inspiring talk. Thank you for everything you're doing for science and for women in science. We really appreciate your presence here. There'll be other opportunities for everyone here to interact with Jocelyn, so please take advantage of that. Thank you again.
And can we thank the signers who've worked very, very hard?
Yes.
Thank you.